Hello, everybody. I'd like to welcome you to the CMI webinar series designed for CMI and by CMI. I'm your moderator today. I'm Cynthia Howell, and I am the Education, Training, and Outreach Manager for CMI. And I'd like to tell you more about our webinar series. We have, for today, while we're on the webinar, as I mentioned, we are hosting these webinars by Colorado School of Mines, and we are always looking for new topics. So please do send us your ideas because these are designed for you. This is a public webinar, and next week you'll be able to find this webinar either on the YouTube series that we have under the Critical Materials Institute or on the webinar menu at aimslab.gov. We are going to be holding questions until the very end of the presentation, and your questions can be typed into the Q&A box at any time. I do encourage you to do that so that we'll be ready to answer those questions in order at the very end of the presentation. I'd like to introduce our presenter today, and that's Dr. Michael Young. He's a senior research scientist at the Bureau of Economic Geology in Jackson School of Geosciences, University of Texas, Austin. He has his PhD in soil physics and hydrology from the University of Arizona. Over 30 years of experience in physics and hydrology, land energy interactions, conservation of water and land resources, and more. Recently, he's focused on land alteration and environmental impacts from expansion of energy systems, and I'm sure we're going to be hearing a lot more about that in his presentation. He's co-authored or authored over nearly 100 peer-reviewed journal articles on a wide range of topics, and is also a fellow of the Geological Society of America and Soil Science Society of America. But I don't want to take any more time of our presenters' venue here. So please, Michael, if you wouldn't mind taking over from here, and welcome.
Thank you, and hopefully you can hear me and you can see my slides. Thanks also Cynthia and to Maureen, who have kind of handled all of this startup very well. So my name is Michael Young, and as was mentioned, we're going to talk today about life cycle analyses of electricity generating technologies. Obviously, this is a complex topic. It requires a lot of different areas of expertise, and my co-authors that you see listed here are really the horsepower behind the work that we're doing. Tristan Childress is an economic geologist. Gurjan Gulen is an energy economist. Atah Raymond is he's a mining engineer and has been doing the LCA analyses. And David Chapman is our project manager. And of course, we have a number of grad students that are also very instrumental and really help us to move things forward. So what is the issue? And you know, we see in the news daily, in the media, policy circles, energy transition, energy expansion, whatever you want to call it, there's almost an all of government approach to you know, decarbonizing the grid, decarbonizing our economy, and but there's a lot of other aspects to, you know, environmental impacts and this connection and this nexus between energy and the environment and economics, and how do we think through these? These are really very interconnected topics, you know, and particularly when you are thinking about decadal scales, when you're looking at the global spatial scale, they become really difficult. Of great interest more recently within Congress, for example, has been the supply chain and critical materials. We're seeing supply chains issues daily, and critical materials is a big part of that. And so what we want to try to do then is sort of build, you know, resilient energy systems that can adjust for intermittency of renewables, that are cost competitive to consumers, and with the least environmental impacts, unanticipated negative environmental impacts as possible. I mean, so this is a really huge optimization problem. You know, we want reliable and affordable energy. We want to minimize impacts to the environment, and we want to minimize costs or keep costs, keep them affordable. And that strikes a lot at what the government is thinking about as well in terms of equity and inclusion and things of that nature. So here's just one example of where the supply chain is critical, and this is, of course, the Critical Materials Institute, so it fits very well. And so, you know, we see a lot of these reports from the World Bank, International Energy Agency, USGS, and others. A lot of consultancies are discussing this again almost on a daily basis. If you get E&E News, you just you're just hammered with these news stories of governments trying to handle this and industries trying to handle it, and everybody's essentially pivoting. But we're having, you know, significant shortages of critical materials, and in the United States, you know, there is a desire, at least, and a sort of a policy goal to create a sort of homegrown energy and homegrown materials that's going to facilitate the energy. But right now, you know, we just don't have anywhere near the capacity to do this. So, you know, where are these future shortages going to be? You know, what are the bottlenecks? How can we address them? How can we anticipate them? You know, if we, you know, when we start really rolling out renewables, wind and solar particularly, you know, these are going to require industrial processes to build. So we're going to be really front loading a lot of the environmental impacts when we build the infrastructure for renewable energy. And then as time goes on, you know, the fuel cycle for wind and solar, of course, is essentially free, and it's environmentally free, and it's very low, very low cost, if any. And so looking at the facility life over a 30-year period, that makes a real difference when you're looking at, you know, if you're front loading the environmental impacts at the beginning, but for the next 29 years or so, there's very little impact. These are things that you can account for and are really important in the analyses. It's very nuanced. So as I mentioned before, we want to balance these things. You know, there's no silver bullet on how we're going to decarbonize our economy. And so we need to balance extraction and processing of material. We want to minimize risks to human and environmental health, and we want an equitable and sustainable energy future. And we want to do that all at the same time. So that's kind of that's kind of our motivation. So I've already stated that, the guiding question. And you know, for those that are in the kind of doing LCAs, life cycle analyses, and this kind of work, I mean, it's really difficult to do comparative LCAs and to compare, say, model results and analytical results in journal articles and in news stories and so on, because the underlying assumptions and the boundaries that these studies are using, they are so different and they are so difficult to harmonize that you know, that people are comparing apples to oranges, and then they're getting in front of the cameras and are talking about apples to oranges, and it's very difficult to kind of suss out what are the underlying assumptions. So what we're trying to do is a really science-based, data-driven, side-by-side comparison of different energy and electricity sources using the same boundaries, using all from cradle to grave. So this is from the mine all the way to incorporation and then end of life. And so this is the entire upstream side of the energy, all the way to disposal. And our goal here is to identify the links in the supply chain that are causing the highest impacts, and what are the things that we can do to reduce the impacts. You know, we can all point fingers at one source of energy or another, but you know, the reality is we're going to need all of these. So how can we reduce the impacts? How can we harmonize the energy systems into sort of one program? And so 2 years ago, actually right after COVID hit, Fu Zhao at Purdue gave an introductory life cycle talk to the CMI on the background of life cycle analyses, and it was a really good talk, because it set the stage for how do you set these ideas up, and you know, and you have to have a study goal, as we all think about, and you have to have a scope. And so the study goals for us is to compare comprehensive life cycle impacts of electricity generating options, we call those EGOs, generating the same electricity over a 30-year time frame. And our boundaries is from the mine, from the point of actually extraction of the material, all the way through processing, transportation, incorporation, all the way to the end of life. We are using a functional unit. This is sort of the normalizing factor of megawatt hour generation. And, we're not interested in capacity. We're interested in generation, because the consumer is basically trying to use electrons for their homes and their businesses and their communities. And so it's really the generation that's more important. We're using a base case of combined cycle gas turbine plants. And at a 500 megawatt capacity, at 72% capacity factor, generates about 3 terawatt hours of electricity per year. And so if we are going to compare CCGT, combined cycle, with wind and solar, then we need to take into account the capacity factors that wind and solar are when they're going to be operating. And, wind plants and solar plants don't operate 24 hours a day, because the wind doesn't always blow and the sun doesn't always shine. So what we want to do is we have to size the capacity of the solar and wind, and we have to upsize that so that as it's generating electricity, given its capacity factor, we're able to generate the same amount. Our analyses are including scopes 1, 2, and 3. So we're doing all the direct impact. So in other words, when the electricity is being generated, that's our product of the electrons. There's some, environmental cost to doing this. It's global warming potential through CO2 emissions. There may be acidification. There may be other, there's land occupation. And there's also land impacts for wind and solar, right? Because you have to do construction on the landscape in order to build these facilities, these modules, and these turbines. And we're also looking at indirect impacts. What are the indirect impacts from using electricity and from the materials that are needed to create it? So in other words, we need to generate and extract natural gas in order to combust it in the gas turbine plant. So what are the environmental costs of hydraulic fracturing and the well pads and all of those things that are necessary to produce the fuel to produce the electricity? We're trying to include all of those in the analyses. And life cycle analyses, it's a very interesting topic. There's a lot of different types of impacts. There are about 17 total impacts that are in typical LCAs. This sort of encompasses most of them: water consumption and contamination, GWP, which is CO2 emissions, land use and land occupation, is it direct versus indirect, ecotoxicity, eutrophication, and a lot of these sort of environmental impacts, including biodiversity and ecosystem services, which is not typically considered in a life cycle analysis. And so we're including that, and we're working to incorporate that directly into the LCA. So an ecosystem service is basically the services that land provides or regulates in service to humans. In other words, the soil is involved in creating the plants that we would eat for food. So there's a service that the land is providing to us, and these are all services that are essentially accounted for by natural resource economists and others. And there's been a lot of work that's been done in the last 15, 20 years on actually creating a uniform approach to looking at biodiversity and ecosystem services, although I don't think that the community is 100% there. So here's our problem definition in the supply chain. And as I mentioned before, it's cradle to grave. So on the left side, going left to right, we look at sourcing of materials. This is everything that's needed to basically build these facilities, whether they're critical materials like lithium and cobalt, whether it's graphite for battery terminals, whether it's the concrete, the steel, turbines, the carbon used in the blades for wind turbines, the glass and all the material that's in solar modules and so on. And so where do these materials come from on the planet? They have to be mined somewhere, then they have to be shipped to a processing facility so that they can be converted into usable forms. Well, depending on the material, it could be just down the street if it's a batch plant for concrete, or it could be processed in China in order to make really high quality lithium and cobalt to create batteries. So, those, you have to put the ore inside of a, inside of a railway car, and it goes to the processing where it gets crushed, and then it gets shipped over to China to be processed. And then it gets incorporated and manufactured into components, gas turbines, panels, batteries, and so on. So all of that is done in different places. And we are looking at supply chain and the distance that each one of these plants are located from, say, from the mine all the way to processing. Then, at least for those materials that are processed in China, they then get shipped back to the US and then deployed to generate electricity. And eventually, after a 30-year timeline, 30-year asset life, for example, the materials are then essentially decommissioned, and they are either recycled or they're disposed of. The energy community that's looking at recycling of batteries and recycling of things like solar panels and wind turbines, this is a very, very nascent stage of the process, and getting these things up to scale is a real challenge. And for those in the CMI that are really looking at the lab scale technology development, how to scale this up so that it's readily available and deployable at utility scale, that is the issue. So here's a little bubble chart showing our phases and our workflow. We start off by looking at the inventory of energy and material inputs. This is all these things that are basically going into making of the facility, a lot of gathering and synthesizing the data. We're using a variety of different sources, which I'll talk about. We look at the uncertain parameters, what is the uncertainty range? We don't have 100% knowledge of a lot of these parameters, number one, and number two, and probably more importantly, is that technology is improving these. So if we want to assess how technology improvements could reduce the environmental footprint, we would be able to add uncertainty bounds and around our parameters, and then run the life cycle analyses in some sort of a Monte Carlo simulation. Now, one of the questions that Fu Zhao had to answer or answered was, okay, in looking at, Gabi versus CMA Pro versus OpenLCA, these are the platforms that are pretty much available globally to do LCAs. We're using OpenLCA as our platform, in part because it's readily, it can be readily written into Python scripts, and they have internal Monte Carlo capabilities so that we can run thousands of simulations by having a variance of a range of parameter values within an envelope that we can set. So we're doing quite a lot of Monte Carlo simulations. And then eventually in the end, you have to look at the environmental impacts, and we're using Recipe 2016, which is a way of actually aggregating the impacts and really looking at what those are from a quantitative standpoint. Now, within phase one, which are most of the bubbles on the left, these are all plants that are isolated from one another. So they're not connected to a grid, right? They're not leveraging off of one another. When we get to phase two, which is this sort of purple bubble on the bottom right, we're going to plug this into a grid, a dispatch model, so that we can see what is the optimum mix of baseload power versus renewable power. Where do batteries fit in, how they fit in? What can we use as the optimum mix that improves reliability, right, and sustainability and resilience of our grid. So for those who are in Texas who are reading the news, we had our somewhat of a grid failure about 18 months ago. How do we design a grid with a diversity of electricity sources that creates a sustainable and resilient grid system? And then how do we do that so it's affordable to the consumer? Because if very expensive electricity, which we're seeing in Europe, we're seeing in California and elsewhere, this harms people directly. This has a direct impact on people's ability to function essentially. So we want to try to keep this cost competitive all at the same time. So this is kind of our workflow. Within phase one right now, we're looking at 5 different energy types. We have combined cycle on the left. We're looking at wind and solar, 2 of the more commonly discussed intermittent sources. And then we're including batteries. So, we would use batteries as a backup to the intermittency of wind and solar. How does that change? If we add a utility scale battery, 100 megawatts of battery capacity, for example, how does that change the size of the number of turbines that we would need going forward? How would that change the number of panels and the size of the solar generating plant out in, does it go from 1,000 acres to 800 acres? What does that mean in terms of the number of modules that have to get built by adding a battery? Is it environmentally positive or negative by doing that? These are things that we're trying to look at. And it is amazing how many assumptions and underlying information is needed in order to make these side-by-side comparisons. I mentioned that earlier. So what we are doing is every graph and every output, we have a table that accompanies the output so that we can see exactly what the assumptions are. For example, what is the size of the CCGT facility? Is it 30 acres or is it 10 acres? That has a big impact when you're looking at, at the amount of the wattage per meter square that you're in terms of your power density. What's the wind? How many acres per turbine are we talking about? Is it, what's the capacity factor? What are the number of facilities? And you can see in wind, this has a lot to do with the size of the turbine itself. Is it a 2 megawatt capacity or is it a 5 megawatt capacity? That changes the number of turbines that are needed in your field in order to generate 3 terawatt hours a year, which we are assuming is our target generation. We assume 30 years for both facilities. We are including replacement. So after 10 years or so, if the solar panels have to be replaced, we include that. If the wind turbines have to be updated, or to be just serviced, we include the servicing of the construction people that go out and they drive out there a certain distance, and then they have to put a certain amount of lubrication in the turbine, and we include even the lubrication that goes into the turbine. We're including the number of wells that are needed to produce the gas to burn in the CCGT plant to produce the electricity. And so as the production levels decrease in the gas well, new gas wells are needed in order to keep the gas production up to a level sufficient to generate the electricity. So we're including the new wells as well. All of these things, I won't read all this, but you can see all the things that we're including for wind and solar. And we'll be doing the same thing for solar. We don't have solar ready yet, and we're using 5 different types of solar panels in order to do the analysis. We hope to have that done by the summer. So here's where we get our data, peer review published reports, papers. We're using data scraping with AS Review. It's a kind of a machine learning approach that uses natural language processing. We're using journal management software. We're talking to battery manufacturers. We do a lot of work in fossil energy here at the Bureau, so we have a lot of people here who know what the production rates are going to be per well. We are using OpenLCA that I mentioned, and we're using EcoInvent, which is a commercially available database that allows us to control and add and modify the data that's going into the database with the information that's coming from these different sources, and I've listed them all here: NREL, NETL, United Nations, Benchmark, UNEP, and a number of others. So we're using as many of these as we can to create the primary data needed to backfill gaps in EcoInvent. I didn't want to, I was a little kind of debating whether to show this, but it's this kind of goes through the same sort of workflow. And so we build all the processes in OpenLCA. We look at the systems for each energy option, and then we assess the impacts using Recipe 2016. All of this information is then processed, post-processed, and then it produces graphs. And then the real question is, well, how do you, what are you actually going to show as your results? So, this is a kind of an ongoing study where we've been going for about a year, maybe 9 or 10 months. So this is sort of where we are right now today. So sure, it would be great to have it all done, but this takes time, and so Lithium and cobalt are completed. So we had 2 master students that graduated this spring, and they are now off doing great things. The CCGT is completed, including the fuel cycle. That's the startup and the replacement, including wells and the facility upkeep. We've completed the wind. The solar is ongoing. We've added up to now 5 technologies, and we've done preliminary work on the batteries. And so we're working with utility scale battery manufacturer to make sure that when we size the battery, we are adjusting the size of the facility itself. We're dealing with discharge rates of the battery. So how often are the batteries discharged? What are the cycling on and off, and how does that affect the life of the battery? So these are all sorts of things that we're doing, and we're solely in the red box right now. Okay, so this next section here of the results was re-recorded so that we could correct a conversion error, which we found just the day after I did the original. And so with that said, here are the preliminary results we're going to talk about. And we have 3 basic chunks of information that I'll provide. The first is a side-by-side comparison of CCGT versus wind energy generation. So we're just going to, with the same boundaries, same analyses all the way through, so we can see where in the process, in the supply chain process, is the environmental load the highest and the lowest. We're going to look at estimated GHG emissions for different transition scenarios. In other words, if we're going to transition from gas and coal to renewables, what does that mean given the speed of the transition if we're looking at 30 years, if we're looking at 20 years, and so on. And so we'll talk about that because that matters a lot as we're front loading the environmental impacts on the renewable side from the construction. And then finally, we've done LCA for lithium and cobalt supply chains. So this graph's a little bit complicated, so I'll spend a couple of minutes on here. The x-axis is the scenario that we're testing. We're testing basically several different scenarios. So the blue bars are the CCGT, these blue bars here, and the gray bars are the wind scenarios. And so down here on the X, you see there's 9 wells per pad, 5 wells per pad. So these are the scenarios that we've set up, and then these are the size of the turbines: 5 megawatt, 2 megawatt, and so on. And the first number here after the underscore has to do with the multiplier that we are applying to the wind turbine itself. So in other words, the scientific consensus on what is a direct impact from wind energy generation is not really there yet. In some cases, it's really just the swept area of the turbine itself, and others are assuming it is some multiple of the swept area. So we're putting in here, say this 5MW_3X would be 3 times the turbine diameter that we're using in our analyses. And here's the turbine diameter, 2 megawatts. That would be 90-meter diameter. And for a 5 megawatt turbine, it's 128 meters. So it'd be 3 times that as our direct impact. And then we have a buffer. So again, the ecosystem and the biological community uses a buffer as an indirect impact. It's a measure of the transition from direct land change to essentially pristine land. And very often it's in the 100-meter range. So we've added that for all the scenarios. In some cases, we're testing this. There's a 100-meter buffer around a 2 megawatt turbine. We have a 100-meter buffer around a 5 megawatt turbine, and so on. So this way we're able to sort of account for the direct and indirect impacts. On the left axis is the total land that's going to be used over the 30-year period, and on the right is sort of a new parameter that we're posing here. We're calling it lifetime generation density, and it's in units of megawatt per meter square. My little it's hidden there, megawatt per meter square, megawatt hour per meter square. How much electricity is actually being generated by these plants? So we're not interested in the capacity. The typical traditional power density calculations are very often done on the capacity side times capacity factor. We're very interested in what is the upstream needs for the fuel cycle to generate the electricity. Now for wind, the upstream is not as much of an issue because the wind doesn't have any kind of a land impact, for example, but for gas it does, because we have to drill additional wells each year to backfill the decline curves that we have measured in the wells out in our study area, which is out in West Texas. And we are using certain capacity factors. You can see the capacity factors on the bottom. Now, so what you see here is the sort of the orange dots show a decrease in the lifetime generation density. Again, this is the amount of megawatts, amount of power that we are able to generate per land area. And the highest lifetime generation density is this 9 wells per pad. So we're really packing those wells into a single pad area that's 3.7 acres in size. So that's a small land area with a lot of wells, and it's generating a lot of gas, so that the generation density is going to be higher in those cases. And as we decrease the number of wells per pad from 9 to 5 to 1, you can see this generation density decreasing. Now, the same can be said for wind. So if we have a larger wind turbine with no buffer and a relatively small a multiplier, well, we have a higher density, but still the values are much lower. So here we're about 5 and here we're about 18 or so, maybe 22. So you can see that the power density of natural gas really matters in these numbers. It's a very dense fuel, and so therefore it would take less of it in order to do work, and the work is where you're turning the turbine to generate the electricity. If we go all the way to the right, you can see this bar is a lot of land area that's being used for the 2 megawatt, 8 times the diameter. So this would be 8 times 90 meters of diameter. Is a large area, and it's also basically has that buffer in there. And so these are very often the kinds of numbers that are published for power density calculations by a number of researchers in academia. And these numbers are really quite small. They're actually much less than 1. So there's a big difference between these values. We have very high generation density, and over here. So these are the things that become really quite important to sort of think about. And if we want to look at this and how this changes in time. So in other words, in year 1, when we start generating electricity, we have the turbines that are installed. It's taking up a certain amount of land area. Here we have 2 megawatt turbines with 3 times the diameter. And you can see that it's requiring quite a lot of land because we're taking up the land without yet having generated the electricity. Once we start to generate electricity, each year we're generating 3 terawatt hours. The cumulative generation begins to increase, and it reduces the fraction in kilometer square per terawatt hour, which is basically equivalent to meters square per megawatt hour. And by the end, we have about a 15-fold difference between the gas right down here in the sort of peach or orange color and the 2 and 5 megawatt turbines. But what you're seeing is you start getting relatively low amounts of land use. It's actually less than 1/10 of a square kilometer per megawatt hour when you are generating for natural gas. So it's, again, that is essentially emblematic of a very dense fuel versus a much lower density wind. So I want to show this again because this graph because we are also partitioning the total land impact and the total environmental load overall for all the different factors that we've talked about. And we're subdividing all of those into these 5 processes, from sourcing of the materials to converting the materials into those things that we need to manufacture the components. We deploy our technologies into the field to generate the electricity, and then we deal with end of life for land allocation. And we're doing this right now for wind and for combined cycle gas. So this is what this looks like for a variety of different environmental impact pathways that relate to ecosystems. And so this would be equivalent if we had human health, if we have ecosystems here. This is what I'm going to show today. And here are the 5 different processes that I talked about: sourcing, processing, manufacturing, and so on. And these bars all sum up to 100%. It's very difficult, of course, to compare these because the units are all different, right? So this again, there's just so much data. All the data has to be intercompared in some way. It's difficult to do. But we are now showing this as a percent of the total, like where is the attribution actually occurring? Under freshwater ecotox, you can see it's under sourcing. It's very much under sourcing for marine eutrophication and so on. But when you get into the operations for combined cycle gas, the global warming potential basically overwhelms. This is the CO2 emission. You know, you're combusting natural gas, you're going to be releasing CO2 to the atmosphere, and you're getting a much higher, almost the entire attribution is occurring during the combustion and the operation of the facility, as well as the land use. So here's the land use that's required for drilling the additional wells to produce the gas that produces the electricity. So this is where the supply chain becomes very, very important. Now, in contrast, we look at the same scale for wind energy generation. And you can see that nearly all of the impacts, all of these orange bars are essentially stemming from the processing of the materials that are needed to build the turbines and all of the functions that are inside the turbine, all except land use. Because as we showed before, this is where we're actually using the land in order to host the turbines. The percent of this, which is somewhere in about 60% of the total land use here, really depends on the assumptions that we're using. So it's really important to think about what are the boundaries that you're using, what are the assumptions you're making in terms of the size of the turbine, are you including the tower and some multiple of the blade diameter, that swept area that we talked about earlier. You know, this is where the assumptions become very, very important, and where the comparisons are being made. And so what happens if we want to change the rate of the transition as we decarbonize? So if we want to look over over 30 years, mid-century, this is the total CCGT. There's a PV, this is the, and PV with batteries, and then we have wind and wind with batteries. And you can see that there's, you know, that the CCGT, basically in CO2 emissions, that once you get the facility up and running, you know, you have essentially a steady rate of the CO2 emissions. For example, for wind and solar, we have to replace the components. And so, you know, we're having to replace batteries and solar panels, and you can see these little blips here. And then we have to do large scale replacement, and then we see much, much larger periods when we go through replacement. So for, you know, so looking at this becomes quite useful, I think, for looking at CO2 emissions. If we want to do this over 50 years, and we include coal in here, so there's coal generation, you can see that the CO2 emissions is quite high as it tapers down, and the emissions from the gas plant, that tapers down. But if we want to really quickly and more rapidly decarbonize, we have a much more CO2 emissions for our renewables than we did earlier on, and also for the replacement. So we want to be able to account for this going forward, as we sort of contemplate how quickly to do this. I mentioned I'm going to show you a little bit of the results from our two students. Zach Harner did the lithium, Andrew Kleiman did the cobalt. And so for the lithium supply chain, we use two different scenarios. One is a traditional scenario with lithium being mined in either South America or Western Australia. It is then put onto a boat. It's sailed across the ocean blue to China, where it's processed. It's incorporated then into batteries, and then the batteries are sent over to America. If we look at the American scenario, then everything stays within North America and South America. The question is going to be, how does the change in the supply chain distance, which, by the way, some of these supply chain distances are 40,000 kilometers of distance that the material has to move in order to actually be deployed. So it's really amazing how far this has to go. So if we look at just the GWP per kilometer, per kilogram rather, of lithium carbonate and lithium oxide, you can see the difference. And just note for lithium carbonate, the y-axis is quite different. So for lithium oxide, it's a much higher amount of GWP for that technology. And you can see right away that there's, you know, that the distances going from the traditional scenario, which is mostly in South America and Australia going to China, versus the American scenario, which is in South America to North America, you can see that the distances on the sea transports are much, much lower. So a lot of this has to do with transportation, but it also has to do with where the processing is done. So in China, the processing is done with a grid mix that is dominated by coal and more recently now solar and wind, but or natural gas. But right now it's mostly coal. So we're assuming we're using the current energy mix in China in order to do this, and the current mix in North America. And you can see the same thing for lithium oxide. As we move to the American scenario, we cut the electricity used for the refinement very, very low, and in some, the truck transport actually goes down to zero for lithium. We do the same thing for cobalt, and here are the supply chains. So the cobalt is being mined primarily in the Congo, but there is soon to be a facility opening up in Idaho here, possibly by later this year. 90% or 95% or somewhere in that area of the cobalt is processed in China, and then it is sent over and back over to North America to be used. That is one. So it's basically the DRC to China. There's the DRC to Finland. So this is the processing facility in Finland, which is owned by Jervois. And then there is the DRC to Canada, where there's a processing facility that I believe is going to be opening up in Canada later this year. And so that's the supply chain over there. And so this is what this looks like if we use China as the base case. This is the amount of kilograms of CO2 for each one of the different components in the processing and transportation for creating a kilogram of cobalt. And as we move from China and over to North America, we can see the reduction, for example, in the electricity use as we change to the North American and as we change to the European scenario. So just changing the location alters not only the grid mix where the processing is done, but it also changes the transportation distance. All of these become quite important when you're doing this comprehensive LCA. Now we study quite a bit. What is the relationship of these scenarios? Are they linear? In other words, if you cut the travel distance in half, does that cut in half your environmental impacts? In some cases it does, but not always. So that the decline in the ore grade for cobalt is a nonlinear function where the kilogram of CO2 produced is non-linearly related to the cobalt grade. So if you get less than 0.3%, you start to have a non-linear increase in the CO2 that is emitted per weight per mass of the cobalt that's produced. So this becomes rather important if you have a higher ore grade early on in the life of your facility, but the ore grade declines with time. You're going to start to have a consequently higher CO2 emissions. So these are things that are this is where we run the Monte Carlo. So I want to talk a little bit about the phase two. We are intending to really look at the dispatch of electricity using a mix of these different technologies. We will have load centers. We're going to sort of our facility locations will be in Texas right now because ERCOT manages the grid and the electricity generation and dispatch here in Texas. But theoretically, this could be moved anywhere. And so the dispatch modeling will be for system optimization, but also to minimize the overall environmental footprint throughout the entire supply chain, depending on what the grid mix is. We will be starting that this summer, and we hope to complete that within a year or so. But that's probably a bit ambitious. Anyway, and then eventually we are going to replace the levelized cost of electricity with a more comprehensive mix metric that we call the consumer cost of electricity. If you include integration costs, if you include incentives, government incentives and tax abatements, how does that actually change the cost to the consumer? LCOE has its benefits in some areas, but it can be sort of misused into thinking that it's just the cost to run the facility, when there's all these other aspects that have to be accounted for to deal with intermittency, to deal with integration, to deal with all of the other aspects that become important. So we intend to do all of that. And so Gurjan Gulen, our energy economist, has done a lot of work on this, has developed the matrix, has published on it extensively. So we're kind of coming to the end of the story. What are the key takeaway points? There's an importance to look at more than just GWP, CO2. We want to look at climate, air, land, and water. Climate is obviously a global issue, but there are also local issues that our communities are dealing with, and the communities are going to have to deal with as this transition continues. How can you minimize what those environmental impacts are going to be? Because if you have unhappy neighbors, you're going to have more issues than if you account for that early on. We want to make sure to account for it. The system boundaries need to include cradle to grave. If you include just one element of this, very often you're missing these nuanced outcomes, which I tried to show. The temporal element is a big issue, particularly when we're looking at different energy sources that are going between baseload and intermittent. And then these really show where we can strengthen these weak links in the supply chain and in the fuel cycle. How can we be able to get more energy for our communities and our countries while essentially maintaining and reducing environmental impacts? Kind of going forward, the technologies that you all are developing really at the lab scale and the bench scale, these are all going to be scaled up at some point. They're going to be deployed broadly. We would like to be able to include those in an LCA approach so we can get a better sense early on. All right, here's where you're going to have more of your tension in your system. How can you scale up this while reducing what the impacts are going to be? Are there economies of scale? Are there those kinds of things that we can be thinking about? And so, becoming, members of CMI, even if we're, sort of junior members of CMI, allows us to basically see how the technologies are changing so that we can incorporate them in this analysis. And then we would like to be able to get this to our audiences, which is the academic community, it's policymakers, and it's the general public and energy providers, so that everybody is using the same script and the same information when they're talking about this. I think that that's half the problem, is different stakeholder groups are using different types of data, and it's really, really challenging to harmonize that. And so here's our team. It's really an awesome team, and our sponsors for our industrial affiliates program are listed here. We're very grateful to them. You're doing a talk, you got to put a sunset picture in a talk, right? So I put a sunset picture in there, even though it's not meant to imply solar. It's just the sun. And so with that, I'm done. I'm open to any questions. There is one here. Will you be able to share the presentation deck? And I believe that the deck is going to be, this is going to be available on the CMI webpage. But contact me. Some of the data that we have here is we're still kind of processing data. So depending on Han, if you need this, contact me, and we can kind of talk through that, no problem. An ex ante. So what do you think are the pros and cons of an ex ante LCA? I actually am not sure what is meant by the pros and cons of an ex ante. If Hung Yu could just describe that, I'm happy to answer it, and try to give some thought to that.
And Michael, while we're waiting for Hung Yu to either give just a little bit more of a descriptor, I basically, again, wanted to thank you for an excellent presentation. And this is no small task that your team is taking on, regarding supply chains and life cycles of energy systems and sources. And then also your final attempt is and desire is to reduce a lot of the environmental and water impacts, so on and so forth. So it's huge. It shows that it takes a tremendous amount of partners to even gather all of this data. What a huge task. But right now it looks like Hong Yu has added a little bit more of a descriptor here for you.
Yeah, thank you. And so, yeah, I think that, this, we would be really happy to take a look at the technologies as they're being developed. I don't see, quite honestly, I don't see any con of doing an ex-ante LCA. I see only pros. And that is, the decisions that we're making here are, in our energy choices are very, there's a lot of unintended consequences. And what we want to try to do is anticipate those going forward and plan for them. We don't want to suddenly realize, rats, we got it wrong, and we just spent $1 trillion changing something, and then we realize that we actually have made the situation less stable. So any place that we can, we can anticipate where the supply chain bottlenecks are going to be, where there's going to be a larger tension on environmental impacts. We want to anticipate those up front. It takes a little bit of effort, but the cost that you all and the time that is being spent to develop these technologies, commercialize them, to seek the funding, to do the testing and the benchmarking, for all that we did in the last year, it's really a drop in the bucket compared to all the other efforts that are going on in there. Okay, so what are the different solar technologies that we're considering? Mentioned 10-year lifespan while the manufacturers give 25-year warranties. Yeah, so that's an excellent question. We're including 5 technologies: monocrystalline, polycrystalline, cadmium telluride, and 2 others, which Ata would be able to remind me of. Unfortunately, he's just a static picture on my screen. So we have 5 of those going forward. We are altering the lifespan for replacement of the panels based on the manufacturer's recommendation, as well as on particular percentage declines per year. So what I showed you was just a preliminary number. As the lifespan increases up, we would be basically using those as replacements. And so the exact lifetime did we use? I think it was a full replacement in 20 years, but we have some modules being replaced in between that period. And again, this gets right into the weeds. For the CCGT, it is a full 30-year, although a lot of CCGT facilities can go up to 50 years. So I think we're trying to harmonize everything at 30. And it would be the same for the wind turbines. I believe that's 20 years.
We do have time for an additional question if anybody might have one, but again, I'd like to thank you again, Dr. Young, for such a great presentation. Tremendous amount of work going on in your direction, and so delighted that CMI can even be a part of this. And I want to tell say thank you to all of our guests as well while we're waiting. The recording is going to be available next week at aimslab.gov or on the YouTube channel. We will have the next webinar will be in August, and details will come in critical times as usual and on social media, so stay tuned. Please let us know if you have any additional suggestions for webinar presentations. Again, they're designed for you and by you, so we certainly want to serve you however we can.
And thanks also to the CMI for allowing us to be part of your day.
Yeah, great. And then it looks like Stacy Joyner has a thank you so much, Michael. So again, thanks everyone, and we'll look forward to seeing you in August for our next webinar presentation.
Thank you.